Hello, friends. Welcome to another episode of Fun Times in Statistics. As always, I will be your host. My name is Rochelle Barr, and I like math. I don't know. Today's episode will be a Minitab 18 edition, so I have some data over here opened on chocolate preferences. This data is from minitab.com, just so we're clear, and is for free public use if you want to go find it. However, I won't be using this data until later because I've got a lot of examples to get through. Woohoo! Okay. So I'm mostly going to be, although it says I just did the mistake, chi-square tests on Minitab for our title. Specifically, I am going to be doing the goodness of fit tests today. So I will have a second video on doing the one for independence that you can view after this one. But let's get this party started. So in your lesson for this week, you did see some you did see me calculate some chi and p-values on there using Minitab. So for this first example, that's what I want to show you, how to calculate some p-values using chi-square. So I'm going to do calculating, just the p-values for degrees, certain degrees of freedom. And then, oh no, I'm going to have to pause. I apologize, ladies and gentlemen. I accidentally didn't save the most current version of this file, so I had to go load the correct one. Notice it has two more parts to part A, and there's some stuff later. This will be the one that I post along with this video. I am sorry about that. I noticed my mistake when C and D weren't there. So I'm going to be doing two things for you. I'm going to calculate some p-values in A and B, and then I'm going to calculate some critical values or cutoff for when we have significant evidence against my null hypothesis in C and D. So we're using a lot of C and D in the video, but I want you to be aware that in your homework, both the p-value approach and the critical value approach will be used. Remember, it's a right-tailed test, so I'm always going to be doing right area. So unsurprisingly, when it comes to calculating probabilities like we are for the p-value, we're going to be using graph, probability distribution plot. And then, as always, we're going to be using view probability. It's the VP of statistics. More awkward when I'm talking to no one. Yep. So first of all, the distribution we want to be on is chi. Remember, you can roll this up, and it is in alphabetical order, so the chi-square will be on top. It's just going to ask you for your degrees of freedom. Since I'm doing A, my degrees of freedom is 3. And then I'm going to hop on over to shaded area. Now, since I have a value of chi, I'm going to change my radial button to x value, leave it on right tail. You're always going to be using right tail with the chi-square values because that's the only thing we're ever going to use when it comes to an additive test like chi. We're going to go from 4.467. So this would be if you had done your setup for your observed expected, calculated your chi value by doing your observed minus your expected squared divided by your expecteds for your categories, and then added them all up. Now, since my degrees of freedom is 3, you want to be careful here. It might be that you're doing a goodness of fit test and you have 4 categories in your categorical variable, or it could be that you're doing a test of independence with a 3. No, how would you get 3? It'd have to be a 4 by 2. Don't worry about that so much. What's important is getting this p-value. So there, ooh, that's a big one. So for me, this p-value, this probability, ooh, would be 21.53. Let me make that a little bit bigger because that's kind of hard to read. And I usually do these in red so you guys can see them real good. Cool. So that would be my p-value for this first type. So this would be, if I had my chi-square test statistic and I had my degrees of freedom and I just wanted the p-value rather than figuring out the cutoff. Cool. So next up, I'm going to do the same thing, but with a slightly bigger degree of freedom and a slightly larger value of chi. So since I just used the chi-square test to do this, or sorry, the probability distribution to do this, I'm just going to hit the Edit Last Dialog box to bring it back up and change some of my settings. So in part B, my degrees of freedom is 13, so I'm just going to go ahead and change the degrees of freedom to a 13. I'm going to click over to shaded area. As always, right tail, and then I'm going to put in my x value of 11.87. Let's go ahead and hit OK. Ooh, much bigger. Ooh la la. Now, one of the things about chi is it usually peaks about 2 less than your degrees of freedom, so I knew this was going to be close to the middle because it'll peak at about 11. And this is very close to the middle, so I kind of knew this was going to be a big p-value, but at the same time, I was surprised how big it is. That's really definitely something that's going to be a fail to reject if this was a real test, but I just made up these values. So there's that. So 0.5383. Cool. So if you were doing the p-value approach, this is one way you could get the p-value. As you're going to see in some of my later examples, Minitab is going to give you the p-values. You won't necessarily have to do this, but when it comes to some of your calculations by hand, you might want a critical value, in which case we're moving on to C and D. So remember, critical values are going to be chi-values that give you a cutoff for when something is significant evidence against your null hypothesis. So if you get a value that's bigger than the chi-square value, you're going to be looking at something that is unusual. And if you're getting something that's lower than the chi-squared value, you would be getting something that's not unusual. So I'm going to click into D. Oops. Or wait, C. I'm doing C. I am using the same distribution, so I could hit edit last dialog and change my settings, but I think I'm going to go back into the menu to remind you where it is. So we're going to go into Graph, Probability Distribution Plot, over to View Probability, and hit OK. Got our degrees of freedom here, and for C we're looking at a 3 for our degrees of freedom. And our alpha is 0.05. So what's different about this is I know my probability and I'm finding a value this time. I'm not finding a probability like a p-value. So I'm going to click over to shaded area, change my radial button to probability since I know the probability is 0.05 for my alpha value, my cutoff for when something is significant evidence against the null hypothesis. And 5% is our usual value for this, so this is usually what you're going to end up doing. We do want right tail because it is chi, and chi is always a right tail. Let's go ahead and hit OK. All right, so it appears our critical value of chi, and here I'm going to be careful. I want the actual chi symbol, so I'm going to steal it from up here in B by just copying and pasting. We'll make it red and big because that's the appropriate symbol for chi. Oh no, it wants to subscript it. I do not want that. No, I don't want to subscript my subscript. Oh no, this is going badly. Okay, I'm going to pause for a second while I fix this. I apologize for that. I really just couldn't get it to format nicely. So my critical value is 7.815. So if you go to do your test statistics, so do your observed minus your expecteds squared divided by all of your expecteds and then add them all together. Not all of your expected, sorry. That was bad. By the expected for that category and then add them all together and got your chi test statistic. You would compare it to 7.88. So I'm just going to write a little summary here. Test statistics being greater than 7.815 would tell us we would reject the null hypothesis, because that would be stuff that would fall in the rejection region over here. If I did my test statistic and it came out less than 7.815, that would be something we would fail to reject. So if you like this approach, you can totally do it before you even calculate your test statistics, which is kind of nice. All right, let's do one more. I'm not going to write a summary for this one, but I am going to steal this sentence because I'm going to need it. And you saw how much I struggled to get Word to do what I want there for a minute. Yeah. Okay, so for this one we're going to have a much larger degree of freedom and a much smaller alpha. So I'm predicting we're going to get a much larger critical value off this one. So I'm going to hit my edit last dialog box, change my degrees of freedom to 9. So this would come off a 4x4 if you were doing something that was a 2 variable or a independence test, or something that has 10 categories with 1 variable and being a goodness of fit. Let's go to shaded area. And here I want 1% instead of 5%. Still a right tail, still no probability because I know alpha. Let's go ahead and hit OK. And there we go. That is a pretty large chi value. I don't know if you guys can see that. That one will make it bigger. So 21.67. So my cutoff for when something is significant is 21.67. So if I do my test statistic and I got something that was larger than 21.67, it would be over here on the graph, and we would reject that value. Or sorry, we wouldn't reject the value. We would reject that null hypothesis. If it was something that was smaller than 21.67, it would fall over here in the white region of the distribution, and then we would fail to reject that So one of the stupid ways that I remember this that might help you is if it's red, we reject. If it's white, we don't reject. So red, reject. There you go. Hopefully that helps you in the future in remembering what to do. Let's move on to the chi-square goodness of fit test. So in this case, I'm actually going to have data. I'm still not on the chocolate data. That's like my third or second example. I forget what order this goes in. But we're going to look at something that's fairly typical as an example for a chi-square goodness of fit test. All right, ladies and gentlemen. So this, I already said that. Why am I going to say it again? So we have a real estate agent who works in a metropolitan area in the northeastern United States, and they've kept data on various property sales in the area. Historically, they've had 15% of purchases be condos, 30% townhomes, 40% single-family homes, 10% commercial, and 5% for land. They're thinking that with the change of demographics, they want to see if the current distribution matches what they've seen historically. So what they do is they gather some sample data and find the following table. So what's important about this is you're comparing current trends to past trends. This is a very typical use of the goodness of fit test. And one thing I want you to be aware in the way that I wrote this is, notice I wrote it across, but hopefully you remember that in Minitab, all of your variables have to go vertical. So I'm going to have to write this differently. So I'm going to write type instead of type of property, and then count instead of frequency, because that's who I am today. So we got some condos, we got some townhouses. I shouldn't abbreviate. That's just going to make this harder to read later. Some homes, commercial, and then land. And then I'm going to put my counts in here. I got 89, 121, 78, 25, and 12. So there we go. I always include the type variable or whatever variable describes your different categories in the tables that you create for the goodness of fit test, because it will help you keep track of something we're going to do later. So what I need to do next is I need to type my hose and my haws. So I'm going to write these two different ways. This is something I didn't get I kind of hinted at in the notes, and about how kind of bad it was, but I didn't actually do. Now that I've got a physical example in front of me that I like, I'm going to do this. So your hoe, for this case, your null hypothesis, would be that the current proportions, or trends if you want to say that, match the historical proportions. So what's nice about this is you're saying there is no change. This is the same. There's nothing different happening here, which is exactly how a hoe should look. Null hypotheses are always statements about sameness or equality. Now, let me give you an alternative way you could have written the hoe if you don't like this so much. So this way, I'm not going to advocate once you get your a lot of stuff to choose from, but here you go. So proportion of condos, according to history, was 15%. So there you go. And the proportion of homes, oh no, townhomes, I gotta be careful. So I'm gonna use TH because I need to make this fit, and it's not going to. I can already see it's gonna happen. Was 30%. I believe this was from San Francisco, which is why townhomes are so popular. They're normally not as popular. The proportion for single family homes was 10%. And of course you're gonna hop on me. Let me put like 10,000 enters up here so this is all on one page. There we go. Should have did that beginning. All right, proportion of homes was 10%. No, it wasn't. It was 40%. It's the next one that's 10%. Okay, the proportion for who am I on? Commercial is the 10%. And then last but not least, the proportion for land is 5%. So if you like this, this is one way you could write the hoe that's different. So you don't have to write both of these. One more time, you do not have to write both these. They both say the same thing. But you can see why when we get into larger groups with more categories, I don't want to write it this way. I want to write it more like the first how I wrote. So for my alternative, I'm just going to say at least one proportion is different. Ooh, I got to be careful about which one I'm talking about. Is it the historical ones or the current ones? At least one of the current proportions is different from form the historical proportions. Now, if you wanted to write the alternative like what I did, the second version of the hoe, I'd have to write either condos is not 15%, or possibly townhomes is not 30%, or homes is not 40%, or or commercials is not 10%, or commercials or not commercials, or land is 5%, or some combination of them, like condos and commercials, homes and townhomes and land are all different proportions. So we gotta be careful. At least one covers like all of your bases because it could be a couple of them that are different. And that's why I prefer to write that rather than all the not equal tos and all the these are different or that's different for the alternative hypothesis. I like at least one better because, well, I think it's clearer of what could happen. All right, so now I need the test statistic and the associated p-value. So if I was to do this by hand, at this stage I would have to add these all up to get the total and then multiply them by the 15% to get the condo value, 30% the townhome, the one for single family homes, the one for commercial, and the one for land to figure out what the expecteds would be. But I'm not going to do that. I'm going to let Minitab do it for me. So here we go. So to do this, we're going to go to Stat Tables, and then down to the chi-square goodness of fit test, one variable. And yes, this is one variable measured twice. It's like the paired test because I'm only looking at this variable measured historically versus currently. I've got like some past history data and then a current sample. So it's going to ask you where the observed counts is. It's asking you for the sample. When you click into the white box next to that, we're going to put in the count. It's also the reason why I have a tendency to name that one count because then it matches. Then it asks you for, hey, what's the names of your categories? That's what I put into type. Cool. Now, next you have a radial button selection of what you want to choose. Now, if you think they're all equally proportionate, aka the 5 of them all are equally likely, which would be 1/5 for all of them, you would leave it on this first button. And we are going to do one like that, but not right now. I actually want to specify the proportions, so I'm going to click the last button. Now, I'm never going to use the middle button because it's screwy how it works. I'm going to choose input constants. I always make this selection because it's much easier to type in what you're going to get. So it asks you for historical counts. I'm going to give it the historical proportions. It'll do the counts for me. So for condos, it was 15%. Or was it 15? Yeah. For townhomes, it was 30%. For homes, it was 40%. Oops. For commercial, it was 10%, and then land was 5%. So one thing I'm going to caution you about here is sometimes it will alphabetize this list, so make sure you're paying attention to what order it put it in, because it might not be the same as the order you typed it in originally. Cool. So the last thing I'm going to do is I'm going to check what it's going to output. So let me check the graphs to make sure it's going to produce what I think it's going to. Yeah, I want all those. I remember I like the default for the graphs. So let's check results. Oh yeah, so be careful, always check the results box to make sure it says display test results, because if you uncheck this, it won't give you the p-value and test statistic that we need to answer this question. Let's hit OK, and OK again, and there we go. So we got a bunch of graphs off this that I'm going to ignore for a second, so I'm going to pull them down so they're out of my way, but yet I can grab them easier in a minute. What I want you to pay attention to is this observed versus expected box. So you'll notice it's got the observed that has the values that we entered in. It has the historical values, which it notices are the proportions, and then it has expecteds. So this is what it calculated to be the expecteds. And you can check this by calculating and adding up all the observes and then multiplying by their proportions to see what you should expect to get. I'm going to pause to pull up my calculator and get it to do this. So the first thing I did is I calculated the total, which is 325. And then let's just calculate the one for home since it's in the middle. And you can believe me that this works. Times 0.4. Lo and behold, it's 130. Woohoo! Okay, so next to it are your contributions to chi. This is the fractions you would get from doing observed minus expected, then squaring it and divide by expected. So I'm going to do that for homes just so you can see where that comes from. So I got to take my observes, which is 78, minus 130. Divide that by 130, since that's my expected. Oh, I forgot to square it. Oh no, bad teacher. Darn it, what was my previous value? It was negative 52. So I need to take that and square it. Oh no, it squared the wrong thing. Okay. So I'm just going to do positive 52 since it comes out positive anyway. Divide that by 130. So I get 20.8. Oh no, look, there's 20.8. It appears to be doing what we expect it to. So it's not even appears, it is doing what you expect it to. So what you want to pay attention to in contributions to chi is that the larger these are, the larger it is making your chi-square test statistic, the more significant the difference was. So I did home specifically because it is the largest, well, second largest one on here. That means it is the most different from history, and condos are the most different from history. So I want to go grab, where is it? The chi-square test statistic box. This is what I want. I'm going to copy this and paste it into my document. Woohoo. And it's going to number it because it likes to number things. Good times. So here, just so we're all on the same page, the test statistic for chi is the chi-squared value. So the test stat here is 62.5385, and the p-value is super tiny. So clearly there is a significant difference here. So hopefully you're looking at this and thinking, ooh, that's a small p-value, it's definitely less than 5%. I'm going to be rejecting the null hypothesis. Ho ho ho. It's Christmas time. That's why it's red. I'm joking. Another thing I want you to look at is, I'm going to look at these graphs really quick to help you analyze them. So the orange boxes, those are the values that are expected. The blue boxes are what's observed. So what's interesting about this is you're able to look and see, ooh, there is quite a difference in condos. They appear to have increased, and homes appears to have decreased because what I expected is much higher than what I actually observed. Commercial and land aren't that far apart. You might ask yourself, is that a big significant difference? Condos and I'm sorry, not condos, this is townhouses. Townhouses like has a difference, but it's probably not significant. It's kind of hard to tell. And that's one of the reasons why I like this graph, but I also dislike this graph. It gives you an idea of who you should be looking at, but the other graph is actually better because this is your contributions to chi. It tells you who is the most significant difference, and it accounts for size. So the large size of the category of townhomes actually does make it so it doesn't contribute that much, but homes and condos appears to have a significant difference. So we're going to write something about that in our conclusion. So I'm going to be rejecting my null hypothesis. It appears that things are not as they have been in history, at least by the evidence that we see. The evidence suggests that there is a significant difference in I said the twice, historical sales of real estate. I have a hard time spelling real estate. And the sales now in these categories. I'm also going to specifically say with the largest change. Biggest probably sounds better. In condos and homes. So that's interesting. So if you're a real estate agent, this would be something that would be a interesting topic for you, hopefully, when it comes to suggesting or selecting what could possibly happen. Good times. All right. Moving on to our card example. So this is going to be a little bit of fun, hopefully. We'll see. So I've gone ahead and clicked and opened this so you can see what I've got here. I've got some random playing cards. I'm going to generate a sample of 40 cards and record their suits. So I'm going to draw 40 cards, yay, from one deck. And I've got everybody showing, but no jokers because I don't want that. And hopefully that goes well. And I'm going to draw the cards and then I'm going to pause so I can count them all. So after I draw them, go baby go. It's now got my cards on display. I'm going to go through and count how many diamonds, clubs, hearts, and spades there are and put them in here for my sample. Not going to lie, you guys, I just totally checked this 3 times to make sure I got this right. Cool. Let's state some appropriate null and alternative hypotheses. So if this is a nice fair deck, you should get all of your suits equally. So that's exactly what our hoe should say. The proportion of each suit is all the same at 25%. So the ha for this you could have also written as, or sorry, the ho for this you could have also written as, I think the proportion for spades is the same as the proportion for clubs, is the same as the proportion for diamonds, is the same as the proportion for, ooh, I have a plus sign in there. That was supposed to be an equal sign. Where's my last one? I'm missing hearts. That's what I got. And they're all 25% because they're all equal. So my alternative is at least one suit of cards, sorry, is different. Or if you want not equal, let's go with not equally proportionate. Now, I'm hoping you go draw your own sample and see what you get. I have had it get as extreme as like having one of them being down to only showing up 6 times. I only did a sample of size 40 because I wanted it to be nice and kind of even looking, hopefully, because I'm hoping to keep it that way, but we'll see. Now, to do the expected counts, since they're all supposed to be equal, you can do this by hand. So, since they're all supposed to be 25%, you do 25% of 40 and get 10. So these should all be 10 because they're all equally proportionate. I put 10 in there twice. Woo. Let me mark this in red so you can recognize what I wrote in. Now, if you don't trust yourself to do this, you can let Minitab do it for you, so no problems there. What is the test statistic and associated p-value? Oh, I gotta do my hypothesis test. Well, if I'm gonna do that, I actually need to type these into Minitab. I haven't done that yet. So, suit. And I can't use count because I already used count. So, cards. Let's do number of cards. Yeah, I like that better. There we go. So, diamond, which I have a hard time spelling, club, heart, spade, space, heart spade. Oh my. Oh, if you can't laugh at yourself. 10, 9, 11, 10. Beautimus. All right. Let's get this party started. So again, I'm going to be doing the same thing. I'm going to be doing a chi-square test, but I'm going to be doing a different one this time because I'm assuming equal proportions. So stat, tables, chi-square, goodness of fit test. So this time I want a different variable. I want number of cards, and I want suit. So notice it immediately pops up with this. Now at this stage you could type in 10, 10, 10, and 10, but I want to use the equal proportionate button. So I'm going to click on that, because these are all going to be equally proportionate. And now I'm ready to rock. Let's hit OK. Let's be OK. All right, so you look at this and you're like, so 2 of these appear to have some contribution, but the others are doing nothing, aka they ended up the same as expected. Let's check that out in the table. So you look here and you'll notice the expected counts. I didn't type these in. Minitab knew to do them itself as equally proportionate, so it took that sample of size 40 and divided amongst my 4 groups and made it equal. There's a very tiny contribution to chi here, so that's not a very good sign that we'll be rejecting that hoe. But just to be sure, let's check the test box, the thing we should actually use to make our decision. And it appears that we're right. Or, well, yeah. Let's merge list. Don't merge list, that's what I want. Perfect. That way it doesn't number it. Ah, look, my p-value. It appears to be quite small, and, oh no, wait, it's quite large. Why did I say that? Oh, the chi is quite small. So my test statistic, aka my chi-square value, is 0.2. I didn't finish writing this word. Not statistics, there's only one of them. And then the p-value is 0.8978. That's huge, much larger than 5%. So large, we're going to fail to reject. So when I write my conclusion, I need to reflect that. So I'm going down to E, and I'm going to write my conclusion to support my hoe. So the evidence supports that the suits, I'm going to write 4 suits of cards. You guys ever played 5 Crowns? It's where you get like 5 or 6 suits of cards. It's kind of fun. It's a good game. You should play it. I forgot what I was writing. The evidence supports the 4 suits of cards are equally proportionate in the deck. Woohoo! Yay! At least at the 5% level of confidence. Okay, moving on to our last example. We're finally going to use that data I've got in the columns for this data sheet, the chocolate stuff. So you'll notice I have 2 columns in the chocolate data. One is gender, one is preference. I'm going to be using the preference column only today. So we want to see, is Ghirardelli going to be right with what they expect? So according to Ghirardelli, and I had to do some digging to find this, a popular chocolatier, 15% of individuals prefer dark chocolate, 80% prefer milk, and 5% prefer white. With changing demographics, the agency wishes to know if the distribution matches the historical distribution, or what Ghirardelli claims in this case. So recent data shows the following. and that's where this data comes from. I should have written this better. Regret. I thought I did write this better. Oh well. Let's do our ho and ha first this time. So since it's only 3 groups, I'm going to write it with the proportions this time. So P for, what do I got first? Dark is 0.15. The P for the proportion, not capital P, for 80%. Remember, we use capital P's for probabilities. That's why p-value gets a capital P. Ooh, I didn't write that it was milk. I thought I did. And then the last one is white, because nobody likes white chocolate. We remember this data. We used it a little while ago. It's 5%. Cool. So, ha, ready? At least one proportion of chocolate preferences is different from what Ghirardelli claims. And I still spelled it wrong. Darn it! Spell check. I wrote Ghirardelli 3 times in this. Still spelled it wrong on the 3rd try. Boo. Dang it. I judge myself. Okay, so couple things we're going to get off of this. I have my data in a column, which means I'm going to let Minitab count it for me to produce my observed and my expecteds. Let's get this party started. So we're going to go to Stat, Tables, chi-square, gives us a fit test, 1 variable. Now this time, ooh la la, I'm going to tell it I have categorical data. Click into that box, throw a preference in there. We're going to click down to proportion specified by historical counts and input our constants. So for dark, what was it? 15%? And then, oop, I clicked wrong, sorry about that. And then 80% for white. Oh no, wait, it's got milk next. See, it did the thing where it alphabetized for me without me expecting. And then 80% for white. So be careful of that. It could happen to you. It could happen to anybody. All right, and graphs, results, let's see what we got. It should be set right because I already have it set right. You can always go back and change this too, so that shouldn't be such a big deal. Let's hit OK. Let's be OK. So I'm going to click into the session window to get what I need. Oh, it didn't give me the total. That's unfortunate. Oh well, we're going to type these in anyway. So for observed, you'll get that off the observed column. Dark appears to be 203, much higher than what Ghirardelli claimed. Mike is 114. Mike. Milk. 83. I'm not going to do the total. You can't make me. You just add them. I believe in you. Oh, wait, we can get it off here. It's right there. It's your total sample size. It's 400. Bam. Get that in there. Dark. Where's my expecteds? Ah, they're all the way over here. Expecteds, 60 for dark. Milk was 20. And then white was 300. Really? 302 for white? That doesn't seem right. Because 300, it's supposed to be 50%. Or 5%. I have them wrong on here. Oh no, I need to run my test again. Hold on, let's pull this back up. Yes, yes, yes. Dark, 15%. Milk, 80%. I did that wrong. I feel bad. I gotta fix it. And that one's 5%. Whoops. Let's be okay. Alright, that looks more normal. So this one's the one that's 320. And this one's the one that's 20. Oops. Okay, and our total's still 400. That would have definitely given me some bad test results. Oh well, I'm okay with showing you me screwing up because hopefully it'll make you realize when things are wrong. Because you should be very, very questioning if your expected is 80% and this was the smallest value, just like I had. Okay, cool. So contributions to chi are all enormous. They're going to get the biggest chi value you've ever seen. Let's go ahead and copy and paste it into our document because Ghirardelli's super wrong on this one. So the test statistic. Oh no, it's really small. Or your chi test stat is 671.8 879. This is what happens when you use the internet to figure out what they think is going to happen with chocolate. The p-value is a resounding nothing. It's not nothing, it's just so small it looks like zero with that big chi. Our conclusion is Ghirardelli's like super wrong. In fact, by looking at your contributions to chi with how large they all are, I would go ahead and say that none of the proportions that Ghirardelli said are accurate. So, the evidence suggests that at least one proportion is not as crap, I'm going to screw this up. Poop. Ghirardelli claims, yep, from the contributions to chi squared, we see that none of the proportions match. Ta-da! Which is interesting. So they're really far off. If you're Ghirardelli, you need to talk to your research department because clearly they have no idea. Or you might ask yourself, okay, is Ghirardelli's sales just super different from everybody else's? Let's find out. That would be something worth investigating. Okay, I hope this helped you with your different ways to do the chi-square test goodness of fitness. I'll see you for part 2 when we do the test for independence. Should be a good time.